So I'm David Hollman. I'm not Christian Trott, but Christian is the PI of this project, so I left his name there. I'm over here. But yeah, so I'm going to talk about Kokkos performance portability ecosystem. And I'm just going to start off with kind of a brief justification here. There's this industry estimate that's been pretty solidly refined that counting all of the phases of software design, from the actual design of the project to the implementation of the code, to the testing, to the refinement, to the maintenance, you can a professional software engineer can do about 10 lines of code per hour, per man hour, right? I mean, that says something about how software engineering works. There's a lot of steps in the process. It's not just writing the code, right? And so if we look at all of the new platforms coming online in the next few years, the exascale era, with Intel now having their own GPUs that are going to be programmed completely differently from all the NVIDIA GPUs, all of the different accelerator ecosystems, some that talk about FPGAs being the future for certain applications. There's a lot of code rewriting that needs to happen. I mean, optimistically, 10% of an application. Pessimistically, it can be far more than that, right? Sometimes it can be an entire rewrite of the entire application. And so typical applications, around 500,000 lines of code in our world, and these are in terms of production applications that use large portions of the time on these giant supercomputers. Sandia maintains a lot of these. If you if you multiply this all out, you're talking about 5 man-years to 20 man-years sometimes to do these refactorings, and we'd have to be doing 20 man-years of work, you know, every year or so with the current churn, if we were to write specifically to these platforms, and that's not really acceptable. So if you look at the situation coming up, with all the platforms that the code at Sandia at least, and in general the national labs has to be able to run on. We have Trinity that came online recently. Summit was just recently benchmarked as Summit and Sierra both were benchmarked as #1 and 2 in the world on the top 500 list. Aurora is coming in 2021. And Astra is, I believe, just came online at Sandia. All 4 of these have completely different architectures. This is an ARM cluster. This is going to be Intel GPUs. This was Intel Phi, which, yeah, appropriate response. And this is NVIDIA GPUs, right? And so if we were to do this mapping, right, we have an enormous amount of software engineering effort that would have to go into this for each application to handle each of these platforms separately. And then we're adding, you know, an exponential explosion every single time we add a new cluster, right? And for a number of reasons, that's not really acceptable use of taxpayer money. It's not an acceptable use of funding for any scientific application or framework. So Kokkos is designed to be the go-between here, where we have a layer that applications can write to, and we provide the programming model, right? A restricted set of things that you're allowed to do, that we are confident through expert analysis, through thinking about this for a long time, and working with this for a long time. We provide a set of things that we allow you to do, that we are confident we can map in a performant way to all of these new architectures. And we get our hands on these things a lot earlier than the applications can, simply because we have already built up so many layers of libraries on top of us. And you know, these guys, some of whom have layers in between us and them, they need to, on day 1 of these giant machine launches, they need to be running. They need to be able to get the numbers. They need to be able to get the impressive benchmarks that are going to go into the newspapers, right? And so, you know, this one comes online scheduled to come online in 2021. We've been working with their simulator for about a year now, and we're finally getting our hands on first pieces of hardware in a non-disclosure agreement environment. It's still 2019, so we get a bit of a head start also. So that's another reason to think about using Kokkos. Okay, so I'm going to talk about the Kokkos ecosystem, kind of our abstractions and our capabilities. I'm going to walk through an example. I'm going to talk about some tools, and I'm going to talk about like where several applications, very important applications that are using Kokkos, and talk about where we go from here. What's next in Kokkos and in Kokkos as a programming model. So, what is Kokkos? So we like to use this term, a programming model for performance portability. Practically speaking, that means it's a library. We're not implementing a language. We're not changing compilers, although there's oftentimes we wish we could. But this should be just not the scale of effort that is reasonable within C++. Modifying a C++ compiler is a massive, massive, massive effort. We leave that to the Googles and Facebooks of the world that have budgets larger than the entire Department of Energy for such things. But we do aim to align with developments in the C++ standard because that's the direction that those big companies are going to be going with the compilers and with the optimizations they make. And we tend to try and approach things from a descriptive programming models perspective rather than a prescriptive programming models perspective. If you're familiar with the world of programming models, you know that there's this big debate between descriptive and prescriptive models, and the debate usually goes pretty much the same way. It's everyone, whatever layer of the stack you're at, it's everyone telling people below them they want a very prescriptive model, and it's everyone telling people above them they want to deliver a descriptive model. So we are one of those Legos in that stack of everyone trying to tell each other things, but we certainly to our customers deliver something that's very descriptive. You're not supposed to be able to tell us the number of threads to run on. You just tell us that your work is parallel here, and here's the forward progress model. Yeah.
Yeah. So just to understand, like, descriptive means what? For example, I have whatever structure, meaning apply that function to that structure, but you don't describe exactly how you traverse it or something.
Exactly. This
is the idea.
It's the what and not the how.
Right. Yeah. Okay.
Yeah. So, and this, I mean, I've learned more and more recently that this pattern is repeated throughout software stacks across everywhere. I was talking to some of the very low-level engineers at NVIDIA recently, and so I don't know, probably not very familiar with NVIDIA's infrastructure software stack, but their assembly language, effectively, they have two, really. They have an assembly language that they guarantee will be persistent across multiple releases called PTEX or PTX. And then below that, each individual release of a new card has a non-public assembly language called SAS, and that's what actually gets translated into the micro-instructions that run on the GPU. So there's three layers there, actually. There's the people who actually write the silicon that generates the micro-instructions, and there's the people who design the SAS, and there's the people that map the SAS to the PTEC. And I was sitting, and so this is like super, super far below the stack, below us on the stack, right? And I was sitting at dinner with a PTEX and a SAS engineer, and they were debating about how the PTEX people want a more prescriptive programming model from the SAS people, and the SAS people want to give the PTEX people a more descriptive programming model. So this happens all the way up and down the stack. But we have reasons to believe that we are aligning ourselves in as much as possible with providing a descriptive programming model to the user that restricts them in certain ways that we think are not healthy for scalable software design in a performance portable environment. So, and we work directly with a lot of these libraries. we expand to meet their needs. We move this level of descriptiveness up and down, right? So sometimes the right level of descriptiveness is directly at the linear algebra itself, and you lose information if you translate the a BLAST call, for instance, into loops, right? And then recovering that information within the programming model in order to do an efficient matrix multiply is nearly impossible. It's a very, very hard thing to do, right? And so we have Kokkos kernels ecosystem that sits on top of us, which I believe is on the next slide. Kokkos kernels that sits on top of Kokkos core, and if you have a problem that's already kind of describing Kokkos kernels, so this is linear algebra kernels, this is a lot of BLAST, this is a lot of PAC, it's some graph algorithms, it's expanded on request. We have clients that need things implemented in that ecosystem. We take pull requests in from them. We do collaborations with people to expand the Kokkos kernels ecosystem. But this is what I mean by, and then even above that, we have Trilinos, which has quite a few other, even more domain-specific descriptive programming model features. And so this is what I mean by we kind of vary the descriptiveness, prescriptiveness up and down the stack. But at its core, which is what I'm going to talk about today, Kokkos is this set of parallel execution algorithms and parallel data structures. And then we map all of that to many core GPUs like Intel 5. We map this to CPU plus GPU infrastructure, and all of the different architectures that people need to run on, particularly to have success at the national labs, but in general in scientific computing. Here are a few people, the few of the places that are contributing to Kokkos actively right now. Since this slide was made, I believe we picked up someone, we picked up someone from Berkeley just recently. So quite a large team who have contributed to Kokkos core. We're now at the point where when a new machine is going to come online at a major national lab like Argonne, we're generally trying to go through a process where that laboratory brings someone on to staff directly who's specifically responsible for the performance of Kokkos on that cluster and in that architecture. So I mean, we're at the point that when someone is spending 2 or 3 years of their lives trying to map this model, or several people, onto a supercomputer, it's going to be pretty hard to beat that in an application-specific way, unless you're something of a wizard. So Kokkos core abstractions, like I said, split into data structures and core execution. We have this thing called an execution space, which kind of generically describes the where, and describes the where of execution, and a memory space which describes the where of data, right? We have memory layouts, we have execution patterns. These are all described in a very concept-driven approach, very similar to kind of how the standard template library works within C++ itself. And a lot of this is feeding back into design for future parts of the standard, and I'll talk about that a little bit towards the end. So from an overview perspective, I'm going to go through some of these things a little bit more in detail, but we have parallel loop patterns, parallel reductions. We have execution policies for tightly nested loops and for non-tightly nested hierarchical parallelism. We have experimental support for tasks, microtasking on GPUs, which I will talk a little bit about. It's not really, it's in production. I'll say more about it later, but it's not as general as it sounds to just call it tasking. We're in the process of generalizing, but we kind of need some application drivers to really understand where to invest time in generalizing. We have this view multidimensional array data structure, which has driven the design of MD span and MD array in the standard, C++ standard coming up, with MD span going into 23. So fundamentally we have a philosophy that involves don't make expensive things implicit. So since data transfer to and from a GPU is potentially expensive, we don't make it implicit. There's no implicit data transfer in Kokkos. You have to do it yourself. So you can point to a line and say that's where my cost is coming from. That's, by the way, a big debate within this community of, go ahead.
Well, because I was going to ask that too, because I mean, I'm really sympathetic to like all these different goals, of course, but then is there a tension always between that philosophy and then the idea of this descriptive programming, between hiding costs or making them implicit, but then also descriptive, or is it not really intentional?
Absolutely, absolutely. But I don't think they are opposite directions. I think there is a non-orthogonal component to those pulls, and you really want to pull on that non-orthogonal component as much as you can, right? And this is an example of that, I think. I think that you can be, this is actually, I would say, still a descriptive way of doing a deep copy in a sense. In a sense, you're saying, make this data available on that memory space. But if this data is already on that memory space, this is a no-op, right? It still describes something rather than prescribes something, right? So if this were prescriptive, this would actually involve take the data at this address and move it to that address, or copy it to that address, right? Whereas this is a much more, I can totally understand where you're coming from with that question, but yeah, what you allow or require the user to describe can still have some leeway. There's still some leeway to decide that within the world of descriptive models. Does that make sense?
Mm-hmm.
Yeah. And OpenMP has made similar decisions to this. If you look at the way OpenMP target offload has been designed in OpenMP 4.5 and OpenMP 5, they consider themselves to be a very descriptive programming model. And in general, the whole Pragma programming community thinks of themselves as very descriptive. And they still have explicit data transfer. So yeah, because often going back and forth between, so another project that has done this, same kind of thing that we're doing is the Raja project at Lawrence Livermore, which you may have heard of. They have a layer on top of them called Chai, which is, I don't even know what it stands for, but basically it does the same thing, same kinds of thing as us, same parallel for, parallel reduce type things, except for they don't have this. They don't have explicit deep copy. They have implicit capture of their equivalent of the view data structure, and that does automatic copy. And like the first thing they tell all their applications to do is like turn certain things off, because the first mistake they all make is data goes to the GPU, data comes back to the host, data goes to the GPU, data comes back to the host, on things that really should just stay on the GPU. So we saw that. I mean, we foresaw that. We also saw it in other places, and that's part of our reason for that decision. So anyway, we had generic version of atomics also, and a number of different execution spaces, the kinds of things that we're working with. And we have this broader pool of capabilities. I won't go through any of these specifically, but we can talk more about any of these later if you're interested in them.
Question.
Yeah?
Your views are owning, right?
Yes, unfortunately.
So if I have already some data somewhere, how can I just use the code?
There is a non-owning version of the view. It's called Kokkos Unmanaged. You can give Kokkos unmanaged as the data policy.
So you may have a code where you already have, containers, whatever it is, and then you want to just take a view on that and use your parallel for each whatever.
Yeah.
And that's possible?
That is possible, yes. I personally would, unless you need to use deep copy, if you're already managing the data and moving the data to the GPU yourself and all of that other stuff, I would just use MD-span directly. Because that's actually going into production now. That said, there is a Kokkos unmanaged. That's an example of something I think that we made a mistake on very early on, is that we were not very specific about data ownership.
Yeah, the other thing.
Yeah.
Exactly the same for everything.
Yeah.
The views are not owning in C++.
Yes.
So.
Yes. So view should not be named view.
Whatever.
And just to make sure I understand your answer, like, are you saying that, like, about using MD-span, that Kokkos is like generic code, so you could just not use the one that's provided and switch to the one from the standard? And
Exactly.
Okay.
Exactly. Deep copy won't work, but we will probably relatively soon provide an overload of deep copy that works with MD-span,
Okay.
special versions of MD-span. But yeah, if you already have the data on the device and you just want to use the Kokkos way of accessing it, yeah. All right. So I think we're walking through a specific example here of a CG solve. So this particular example does vector addition, it does a dot product, does a sparse matrix vector multiply. So we can't just directly call BLAST for all of these things. I mean, this third one is sure implemented some places, but it's probably too general. So this is actually a pretty good example. So we want to start with a view. Oh, and here it is, right? Memory traits unmanaged. Also, our PI, for whatever reason, hates spacing, so I apologize for the space lack thereof in these slides, but it makes me cringe. I don't know if it makes you cringe at all, but anyway. And so we already have the data somewhere, so we're going to create an unmanaged view here. We're going to create a managed view for the, which is the default, for one of the intermediates that's maybe going to be on the device, and then we do deep copy here, right? And this will just be a, since this is uninitialized, this is just going to be a transfer of the pointer on the host case, but on the device case, we actually have to set up this memory and move the data over. So we do the optimal thing as much as possible whenever we can in this type of model.
So you say this memory is on the host, the other one is on the, let's say, GPU.
Yeah, and it's part of the type, right? So what this is hiding, since you guys are a little more advanced in your C++ than most people that we give this talk to, this is hiding a default template parameter that's defaulted based on build system things. But you can be actually much more explicit. See, this says host space. We can actually specifically put in there CUDA space. Or if you want to be more general, you probably put this in a function somewhere that gets called with a parameter that is your execution space. Right.
So I could define something on the host, something on the GPU, and transfer easily.
Yep, exactly. Or you can define something on default memory space, right? And then you can change whether it's on the GPU or CPU based on your build system.
Is it important to understand what xn and the string x are doing here, or not so much?
Let's see. Is it important?
Xin is your input data.
Is it? Okay.
Yeah, xn is the input data.
You take a view on it,
Okay.
then you work.
Yeah.
Okay. But in the next one, it's a string? Like that's something else? Or?
What? Oh no, these are just labels. These are profile labels. The strings are just profile labels. I'm sorry.
Oh, no
that's not clear. This is part of the reason why C++ desperately needs keyword arguments. That's another discussion.
Yeah, it does.
I have pushed on the C++ committee for that ever since anyone would listen to it. But so yeah, we need to, for the AX plus Y, we need this simple loop. So here's the serial implementation. We need this simple loop where we scale something up. In Kokkos, you just basically replace this with parallel 4. You have this fancy schmancy macro Kokkos lambda, which is on the host, just translates into square bracket equals close square bracket, right? On the device, translates into, or if you're compiling for CUDA, translates into square bracket equals close square bracket, fancy schmancy device marking nonsense that CUDA makes us do. And on architectures that we can't even talk about right now, has to do some other things also. So you hide that behind a macro for you so that your code is portable and doesn't have to be changed at all as things move forward. And actually, as these new architectures are coming out, we kind of basically demand that they give us something that we can hide behind that, right? So that users don't have to change their code. Go ahead. What's up?
Capture?
Capture?
Can
Yes.
you capture?
This is this hides a capture. Yeah, it's equals capture.
Oh.
It is not reference captured because obviously the reference doesn't make any sense.
That's my question.
Yeah, the reference doesn't make any sense on the GPU, right?
Of course.
So it has to be done by value, and actually that is a problem like inside of a member function of a class because you accidentally captured this pointer, right, by value. So if you follow C++ progress, in C++ 17 we added a star this. So that was a Sandia proposal that came out of Kokkos. So if you've seen the star this proposal that was accepted into 17, that came out of this work.
So the bottom line is that you capture the external context.
What?
You capture
Yeah, you capture the context. So yeah, here we're capturing the view.
That was my question.
Yeah.
That's fine.
Hopefully that makes sense. And maybe I should start writing it for these contexts. I should start writing it as, you can also write it as square bracket equals close square bracket Kokkos underscore function. So if the reader of your code is more aware of such things. So yeah, in Kokkos, all of our fundamental idiom or fundamental pattern involves 3 components. The pattern, oops, there's a string label for that's not fundamental. Pattern, execution policy, and functor. I thought he was labeling these things differently than he is. Okay, you can add a string label for profiling. This is the simplest possible execution policy, which is a shortcut for range policy of 0 to n on the default execution space, right? But n is the shortest way of saying that. But fundamentally, when you look at this thing, you look at the pattern, the policy, and the functor, which is this whole thing, and can obviously be expressed as a lambda. And you'll get an iteration handle, which the simplest version of an iteration handle is just an integer, right? So we have like shortcuts for a lot of these things, but they all simplify to very generalizable patterns. And I think I'm going a little too slow, so I might need to speed up a little bit. All right, so now if we go to the dot product, right, you can't just express that as a parallel 4. And it's this is actually incredibly non-trivial to write in CUDA. If you've ever tried to write a device size reduction in CUDA, it's something on the order of 1,000 lines of code to do it passively, just to do a dot product, and to do it at the device size limit. And to do it optimally, it's can be 5-ish thousand lines of code. You have to do, anyway, there's all kinds of crazy stuff you need to do there. But in Kokkos, it basically just results in this same exact thing, right? We have a parallel pattern, a functor. The reductions in Kokkos output via an argument, which is actually something we did just for performance purposes when we designed Kokkos way back 10 years ago, but is actually an emerging paradigm in programming model design in more general contexts. Facebook is a big fan of this right now for a lot of their software stacks. The same kind of thing. a more general version of this. They're not passing in a reference and then outputting via it, but it facilitates a lot more general programming model patterns in a number of ways. And so that's you can see this is how this is very similar in form to the parallel 4 that we had on the previous slide.
Is this supposed to be x dot y? I'm confused. Where's sum coming from? As the argument to your function.
Right. So we output via an argument, right?
Yeah.
So, because if we were to capture by reference, right, then the reference wouldn't mean the same thing on the CPU and the GPU, right? It's a pointer, right? So this is what I was trying to talk about earlier about restricted programming models, right? We restrict what the user's allowed to do. You're not allowed to capture things by reference in the Kokkos programming model because then it would not be, there's no way to make it portable, right? So, so the sparse matrix vector multiply, this is a pretty good I think he's going to go talk about, yeah. This is a good place for talking about the kind of hierarchical parallelism we might need. So here's the serial version. We have an outer loop over matrix rows, an inner loop over the dense vector, and we're doing kind of random access. And here's the same thing kind of written in Kokkos. So I won't dwell on this because I'm running out of time and have other interesting, I'm less than halfway through and I have interesting other things to talk about. But basically we provide a way to do hierarchical parallelism. We allow you to create teams of threads. Remember I said earlier that the iteration index is the simplest version of the team handle, right? So here's here's the team handle, and the team handle allows you to do hierarchical parallelism on multiple levels. Currently we support 3 levels. I'm working very hard to generalize that and to kind of generalize the naming scheme of them so that it's just a 3-level, multi-level parallelism described rather than prescribed as much as it is currently. And so you can again see it's a little bit more complicated, but you see pattern, policy, and functor, right? And everything, pretty much everything in Kokkos is well, that's not true, but much of Kokkos is code follows this same direction. And we have, even in the nested versions, we have pattern, policy, and functor. You're capturing by reference here because this is allowed, this is within the GPU, right? You can capture by value also, it doesn't really hurt. So performance. Here's some plots comparing us with code written directly to other programming models. And on various architectures, we have AX plus BY, we have a dot product. Oh, higher is better. Like, why are we so slow compared to OpenMP? But no, OpenMP has problems with reductions. I was like, so yeah, higher is better. Performance is in gigaflops per second. Yeah, OpenMP reductions have problems. I think they've gotten a little better since we made this chart, but they're not significantly better. And so you can see that in many cases, we're actually outperforming the native, like how in the world are we faster than CUDA on a GPU, right? I mean, that seems insane, and that's because we know things that a typical CUDA programmer doesn't know. We get some secret sauce from NVIDIA directly. We talk to them a lot. We put in all kinds of little tricks that a typical CUDA programmer is not going to know. Even an advanced CUDA programmer is not going to know. And so we're actually better than zero overhead in many cases, which is a pretty strong statement. And yeah. I'm going to skip tasking, even though it's the part of Kokkos that I wrote. And I'll come back to it if I have time. So Kokkos kernels, I've heard a lot of people that I've talked to so far here say that they mostly just call BLAS. So we have an equivalent of just call BLAS. It's Kokkos kernels. Well, one of the interfaces that we allow very much looks like just call BLAS, except for you use views instead of pointers, and you don't have to do all this D, Z, C, S nonsense because we live in C++ world. Yeah, they're agnostic to scalar type. They call vendor libraries whenever available, so you still don't have to write your code to think about kuBLAS or to call MKL directly. So we handle all of that, and when implementations aren't available, like for newer hardware, we have a reference implementation that's generally, hopefully, fast enough for most purposes. And these can also be called in nested contexts, and in a nested context, we'll do the right thing. So if you're inside, so if you were to just call BLAS directly here, you would the default implementation of BLAS would try and use all of the threads on the machine, right? And if you're already in a context where you're parallelizing over all the threads in the machine, you actually probably just want to use all the threads in the team, right? Which might be, all the threads in the team might be all of the hyperthreads on one thread, or if we're at a place where we're mapping teams to cores or to sockets even, depends on how the problem is set up and how the performance characteristics you need. But in general, this Kokkos kernels works with hierarchical parallelism. We have
Also, question.
Yeah.
Quick question. You map the whole BLAS on LAPAC as well?
Not
I want to do an LU decomposition.
what?
I want to do a LU decomposition.
Yeah, we do have LU decompositions.
So the most common thing.
We have a lot of the most common things. We have all of the things that Sandia definitely needs.
For example, like compute determinants, these sort of
Yes, we're missing a lot of things that a lot of other people need, but if you put in a request, it'll probably happen. Like that team, does a lot of new work, but wrapping something is not all that hard in general. And we have a lot of linear algebra experts at Sandia, world experts in linear algebra at Sandia that do this work very well. Kokkos tooling, we recently pulled on a new David Polyakov, a new staff member who's basically in charge of this now, and is driving this forward at a much faster rate than before. But we provide a number of basic sets of tools that can even hook in via environment variables and via dynamic linking. Some of our applications that we work with are so complex, they take 3 to 5 hours to recompile. And obviously, recompiling in debug mode is not really to recompile the whole thing, not an individual translation unit, but recompiling the entire tool chain just to do some debugging is not really an option for them. So we provided these sorts of tools in that respect. We also have, and these labels that we've been showing along the way, right? These are optional, but if you put them in there, the Kokkos tooling will use them. And so they'll give you a good display. And they interact with a number of other parts of the ecosystem. For more information, look at the Kokkos tooling repository on the Kokkos GitHub group. So everything that Kokkos does can be found on github.com/Kokkos. And so like Kokkos core is github.com/Kokkos/Kokkos. And Kokkos tooling is all in github.com/Kokkos/Kokkos tooling, Kokkos-tooling. And Kokkos-kernels is another important repository there. So if there's something that's not on Kokkos tooling that you want, put it in an issue and someone will address it. If there's something missing on Kokkos kernels, put it in an issue, someone will address it. We have one of our goals on the Kokkos team. One of our milestones is to try and get our issue response time down, our average issue response time below 24 hours. So one of those milestones that we're not really allowed to fail. So if we do, we should be responding pretty quickly. And that doesn't mean that we'll implement your feature in 24 hours, but we'll write a response and say, hey, we'll do that in a year maybe, or no. or we'll write a response saying, yeah, somebody's been working on that for the past 6 months, it'll be coming online in the next 3 days or something, if you're lucky. Yeah, so we also have a Slack, kokkosteam.slack.com or whatever. I think you have to email us to get onto that Slack, but it's pretty easy. So we have a pretty rapid response on the Slack to issues. So DOE machine announcements. So yeah, like I said earlier, we have all of these machines coming on that are all have different programming models and all have different hardware, and it's not really reasonable for people to rewrite their code every time a new thing comes out. We were actually, so this is a funny story here. For the AMD GPUs, I told you guys we get early access to a lot of things. The problem with the AMD GPUs is that we got such early access that they gave us something that they decided to abandon, and we'd already written our backend in it. And then a number of our competitors actually got access after they decided to abandon ROCm. And so several of our competitors are slightly ahead of us on this, embarrassingly, because we did a full-scale implementation of something AMD corporately decided to abandon and didn't tell us until too late. So yeah, that was fun. So we have SQL backends in progress. We have an OpenMP target backend, which is going to hit some of the AMD clusters and some of the newer NVIDIA clusters with certain requirements. And in terms of projects currently running, actual full-on production code, code bases with on the order of 500,000 to 1 million lines of code, we have about 12. And so these are projects that have probably, depending on the project, 20 to 50 developers on them. Production codes that are code bases, excuse me, give me a second, that are in the process of porting, something like 35. Most of those are committed from a funding perspective to getting a working Kokkos implementation up and running and showing results by the end of their funding period, whatever that period is. We now have a number of packages that are in these large collections, things like parts of Trilinos. If you're not familiar with Trilinos, you can think of it as kind of like Boost. Like this would be like saying that a part of Boost is using us. So tpetra is a part of Trilinos in the same way that, I don't know, Boost MPL is a part of Boost. And then a number of other proxy apps, packages evaluating Kokkos. Some of these things are like single research group at some university or something Here's a impressive logo cloud of about, this is about 2/3 of the people collaborating with us probably. Probably half of these people, half of these corporations have at least 2 projects, or half of these logos have at least 2 projects. There's several on there that we can't even talk about yet for whatever reason, but yeah. Boy, what do I have, 10 minutes left? Okay, these are important applications using Kokkos. I will send out these slides afterwards and you can ask these people about their experience, but I won't go too much into details here. I want to talk a little bit about how we've kind of our experience with this process of this cycle of adding a feature to Kokkos, proposing a generalized version of it for the C++ standard, and backporting those versions to something Kokkos can depend on. This was really the process for empty span. This was the process for atomic ref, which was also a contribution we made. So atomic ref allows you to make atomic operations on non-atomic entities. So if you're familiar with atomics in C++, the non-ref versions have to be atomics for their whole life. And if you want them to be non-atomic, you have to move the memory. Well, that's not really acceptable for gigabytes of memory, right? If you only need to do one reduction over the entire lifetime of the data, and all of the other stuff is non-concurrent, all the other axes are non-concurrent, then that's a deal breaker. But this in C++20 we will have atomic ref. It works exactly like you'd expect. All the operations that are available on atomic are available on atomic ref. There are certain requirements on what you can put in there, but all the things that you guys would want to put in there, you can put in there. Floats, doubles, complex, ints, and kind of basic structures. MD-SPAN, if you're interested in MD-SPAN more, I'm going to be talking about that tomorrow morning in more of a kind of discussion feedback format. I have about 20 minutes of slides or so, but we're going to have a kind of open discussion as to how that process goes and how that went. I do have a production implementation of that. You guys this trip was a specific motivating factor to get this thing done in enough time to be here, so that if there's nothing that if you can't commit wholesale to trying to use Kokkos, you at least can take this header-only library, play around with it, see if it gives you what you need for your code. We also are making contributions to linear algebra, basic linear algebra in the standard. So basically, C++ standard BLAS books, which don't look at all like BLAS, but that's okay. I don't think anyone is super attached to the way BLAS looks, only the way it performs. So we are doing this in a way that we are confident that the non-HPC parts of the C++ committee can swallow them, and the performance-sensitive parts of the HPC community can swallow them. So that's the big challenge there. And we have some of the world's experts in linear algebra on that proposal. Jack Gambira from Tennessee is an author on that proposal. Mark Hollman from Sandia, who's led many of the largest distributed memory linear algebra efforts out there, is also he's the lead author on the proposal. So we got together a whole bunch of people who really know what they're doing, and hopefully that's going to work out pretty well. And then executors, I could talk for hours on executors. If you're particularly interested in the history of executors on C++, look up my talk at C++ Now this year. There's a whole lot going on there, and I don't want to kind of give the wrong impression by trying to give a really short summary here. But yeah, just look up my name on YouTube and C++ Now 2019. Okay, yeah, this is about how we are orienting Kokkos towards executors for C++ 23. I'm going to skip that also. Again, refer you to the presentation. Here's a bunch of links. Again, I'll send this I guess I send this to Mary Kate and she'll send it around, or?
Yes, I think we can do that.
Okay, great. Yeah, we have several recorded talks on Kokkos. We have several publications on Kokkos. Like I mentioned, the GitHub is where you find all of our code. And the presentation on YouTube about executors, you're welcome to look up. And I think that's it. So I guess I skipped all the right numbers of things. I hope I skipped the things that you guys wanted me to skip. But questions, yeah?